Now we're going to take up one more problem, the problem number 27. It reads as find the total elongation of the bar shown in figure. Take E, that is the Young's modulus, equals 1.05 into 10 to the power of 5 Newton per mm square. So here you can see there is a section between A and B, which is a circular bar wherein there is a diameter of 20 mm to a length of 400 mm which has been bored inside, and the diameter of 40 mm has got for a 600 mm length, and uniform bar of diameter 30 to a length of 800, and there is a uniform tapering bar, a round bar from 30 diameter to 60 diameter from C to D at a length of 1000 mm. So here at the point A 40 kilonewton is applied, and at the point B, which is P, which is acting towards the right side, and at point A 40 kilonewton is acting towards the left side, and at C the point is acting towards 30 kilonewton is acting towards the left side, and also at D 50 kilonewton is acting towards the left side. So this is the actual problem which has been given. So we want to find out the total elongation of the bar. First we need to find out what is the value of load P. Now for equilibrium of the bar, load acting towards the right side is equal to load acting towards the left side. If you consider the load acting towards the right side, you have only one force which is acting towards the right side, which is P, which is equal to the load acting towards the left side is 40 kilonewton, 30 kilonewton and 50 kilonewton. So 40 plus 30 plus 50, it is 80 plus 40, it is 120 kilonewton. So the P value will be equal to 120 kilonewton. Now first we are going to consider the free body diagram of different segments, which is, so first we have taken a round bar of diameter 40, wherein a diameter 20 mm is bored to a length of 400 mm and the overall length of the bar is 600 mm. So at the point A 40 kilonewton is acting towards the left side. So and here at the point B it is 120 kilonewton which is acting towards the right side because it is P value which we have found out from here. Then we have minus 30 because the load which is acting towards the left side is considered negative. So minus 30, and the load acting towards the left side again minus 50. This is at the point B, this is at the point C, and this is at the point D. So if you take 120 minus 30 minus 40, 80, 120 minus 80, which is equal to 40 kilonewton. So since it is a positive value, so it is acting towards the left side. So acting towards the right side here. So that is the reason why we have taken this 40 kilonewton, which is acting towards the right side. So this is the equilibrium for this particular bar. Now we are going to take the second consideration, wherein it is the point B and C, wherein a uniform diameter of 30 mm to a length of 800 mm. So on the left hand side you have 40 kilonewton which is acting toward the left side, and at the right and at the point B it is 120 kilonewton acting toward the right side. Similarly, so when you are considering this according to the sign convention, so the force which is acting toward the left side is considered to be negative, and the force which is acting toward the right side is considered to be positive. So if you do that, it will be minus 40 plus 120, which is equal to 80 kilonewton. So since it is 80 kilonewton, since it is positive, the force is acting toward the right side. So that is the reason why we are getting the 80 kilonewton which is acting towards the right side on the left hand side of BC. Now when you are considering the force on the point of C, there are two forces that are acting towards on the right hand side. One is 30 kilonewton which is acting toward the left side. Again 50 kilonewton is acting toward the left side. So minus 50 and minus 30, which is going to give you minus 80. Since it is minus 80, the force is acting towards the left side. So that is the reason why you can consider here minus 30 minus 50. So minus 30 minus 50 is minus 80. Since it is negative, it is acting toward the left side according to the sign convention. Therefore, at the point C, you have 80 kilonewton which is acting toward the left side. Now similarly, we are considering the one more, the last one, which is the tapering bar. having the diameter varying from diameter 30 to 50 and having a length of 1000 mm. So the force which are acting towards the left side, which is minus 40 here, and the force which is acting towards the right side is plus 120 here, and the force which is acting towards the left side is 30 kilonewton. So for minus 40 minus 30 plus 120, which will going to be plus 50. Since it is plus 50, it is acting towards the right side. So acting towards the right side at this point, and here, which is again, it is 50 kilonewton, which is acting towards the left side. So 120 minus 70, 40 minus 40 minus 30, which is going to give you 70. 120 minus 70 will going to be 50. Since it is positive, acting towards the right side. So again, you will going to, at the section CD, you will going to have the compressive load. So now we can see that minus 40 plus 120 minus 30, which is equal to plus 50 kilonewton. Since it is positive, it is acting towards the right side according to the sign convention. And since this side is minus 50, so it is acting towards the left side. So the force what you get here is the compressive force. Similarly, when you are considering here, since the positive 40 kilonewton on this side and is also 40 kilonewton on this side, so naturally it will going to be tensile. But in BC, since the load is acting towards each other, so it will going to be compressive in nature. Now we need to find out what are the elongations. Since he wants to find out what is the total elongation. So the total elongation of the segment AB, which is delta L1, which will be equal to extension of on-board section plus extension of board section. So here extension along elongation of the segment AB, that is delta L1, will be equal to extension of on-board section plus extension of board section. So what does it mean? If you are considering here, this can be further divided into two parts. One is the extension of on-board section, that is from here to here, and this as the extension of board section. So what happens here? So delta L1 will be equal to P into L1 by A1 into E1. So here E. So here, since it is the 40 kilonewton, P is 40 into 10 to the power of 3 into L1 is onboard section is 600 minus 400 will be equal to 200 divided by A1 is pi by 4 into 40 square into E. What is the Young's modulus of the material? The Young's modulus of the material is 1.05 into 10 to the power of 5 Newton per mm square. So that is what we are going to get here. 40 into 10 to the power of 3 into 200, that is length of the onboard section, divided by pi by 4 into 40 square, because the diameter of the bar is 40 square, into 1.05 into 10 to the power of 5, plus extension of the onboard section, which is the onboard section, board section, that is from here to here. So this becomes a hollow cylinder, hollow circular bar, wherein again P is equal to 40 into 10 to the power of 3 into length is 400 divided by pi by 4 into 40 square minus 20 square into 1.05 into 10 to the power of 5. So that is what we have written here. 40 into 10 to the power of 3 into 400 by divided by pi by 4 into 40 square minus 20 square the whole into 1.05 into 10 to the power of 5. So on simplification, the delta L1 what you will going to get is 0.223 mm. So now we go for the contraction of the segment delta L2. So what is the contraction of the segment of delta L2? That is P into L2 by A2 into E. So here, since it is a uniform bar section, so what is the delta L2? Delta L2 is nothing but P, which is the 80 kilonewton, 80 into 10 to the power of 3 into length will be 800 divided by A is pi d square by pi into pi by 4 into 30 square into 1.05 into 10 to the power of 5. So that is what I have written here. Delta L2 will be equal to 80 into 10 to the power of 3 into 800 divided by pi by 4 into 30 square into 1.05 into 10 to the power of 5. So delta L2 will be equal to 0.8623 mm. So then again we have the tapering bar, wherein it is a tapering round bar, varying from smaller end diameter is 30 and the bigger end diameter is 60, and the load what you have is the compressive load, which is of 50 kilonewton and over a length of 1000 mm. So what is the formula for this of the tapering bar? The tapering bar is delta L3 will be equal to 4 into P into L by pi into E into D1 into D2. So that will be equal to 4 into P is 50 into 10 to the power of 3, or the length of the bar is 1000 divided by pi into 1.05 into 10 to the power of 5 into D1 is the diameter of the bigger end and D2 is the diameter of the smaller end, which is into 60 into 30. So on simplification, you will going to get delta L3. So what is a delta L3 will be equal to 0.3368. Now, what is the requirement? The requirement is I want to find out the total elongation. The total elongation will be equal to the sum of the individual elongations of the segments. So what are the sum of the individual elongation of the segments? One is the tension along AB, that is elongation of the segment in AB, and then the contraction of the segment in BC, and the contraction in the taper section of CD. So that means you have delta L will be equal to delta L1 plus delta L2 plus delta L3. So here in this case what happens, delta L1 is in tension, so it is positive, and delta L2 is contraction, it is negative, and delta L3 is also contraction, it is negative. Therefore delta L will be equal to delta L1 minus delta L2 minus delta L3. So that is what we have written here, delta L1 minus delta L2 minus delta L3. So delta L will be equal to, what is delta 1? The delta 1 is nothing but 0.2223, and then minus 0.8623 delta L2 and minus 0.3368, which is delta L3. So that is what we have written here, 0.2223 minus 0.8623 minus 0.3368. On simplification, the delta L will be equal to minus 0.9768 mm. Therefore, total change in length will be equal to, since it is negative, it is contraction, and 0.9768 is the total elongation of the entire segment. So this is how you will be able to solve this particular problem. Thank you.